It's great that JJ gave an introduction to the normal pulsating white dwarfs. And so I'm going to be talking about a project that I've been involved with a large number of people, many of which are here in the room, Jan, Boris, Keaton, Odette, Zach. We've been trying to follow some of the pulsating white dwarfs that exist in cataclysmic variables. So these are white dwarfs that are surrounded by an accretion disk, and they have mass transfer from a secondary star. So the whole point of this was to try to see what the differences would be between normal ZZ Ceti or other kinds of pulsating white dwarfs and these systems that have all this accretion happening on them. And they're different because they're rotating faster than typical white dwarfs. Now, yesterday we heard that there are some white dwarfs that are rotating at periods of minutes, but typically these are 200 seconds versus the days that normal white dwarfs, single white dwarfs would rotate. And they're hotter due to the accretion, the long-term effects of accretion, and also that the accretion effects gives them a different composition than a single white dwarf. And so they're, have helium zones more so than a typical white dwarf, at least a ZZ Ceti pulsator would be. So their instability strip is 11 to 16,000. And they have this mixed composition that are typical fit with models that are a tenth of a solar. They're more massive. They're 8/10 solar mass, although we heard yesterday that there's also a group of single white dwarfs that have this little mass peak at 8/10. But generally, these are pretty much all 8/10 solar versus 8/10 the mass of the sun. And the main thing that we wanted to look at is that these things have dwarf novae outbursts. And these aren't the things that JJ was talking about, these little 40%. These are things that are several magnitudes up to, the ones I'll be showing you are up to 9 magnitudes. So typical, a recurrent nova is 9 magnitudes. So these are massive dumps of material that heat the white dwarf for periods of time. But the nice thing about these is they cool on timescales of years, which we can actually follow, versus the long-term evolution of cooling. So we wanted to see what the effects of this could be. Okay, so there's only 18 of these now known. The columns here, I'll be talking about those 3 that have stars by them in particular, the ones that we followed the most. You can see that there's a range that they've only been known for the last 24 years. And the last one down here wasn't discovered in 2017, and so now it's 2022, and we still haven't found any more. So that's one of the things I want to promote, is to look for more of these systems, so we have a greater pool. Most of them have very short orbital periods, near 80 minutes. They're all under the period gap. And as I said, the temperatures range from 10,000 to 16,000. And the pulsation periods are 4 minutes to 20 minutes. So they span the range. If you put them on an instability strip, and if you put them on a log G, they're not log G, they'd be more down near 8.3 or so. But they're still well outside the normal instability strip for ZZ Ceti stars. So how to find these, that's the problem. So years ago when we did the search for Sloan CVs, I made a plot of where the ones that were known then fell. They're blue in color, but there's a lot of other things that are blue in color. So you'd have to look through a lot of these to find the ones that are pulsating. So the clue to which ones are pulsating are the ones that actually show up as a white dwarf in the spectrum. And so they're the ones that show the broad absorption around H beta and higher Balmer lines, because that absorption is the white dwarf. And if you're going to look for pulsations from a white dwarf, you have to be able to see the white dwarf. And in most of the CVs, the accretion just dominates the optical light. But the UV is the much better place to look, because of the UV, the light is almost all the white dwarf. We found over the years a wide variety of surveys of the white dwarfs in CVs. This black is the data from Hubble, and the red is a fit of the blue white dwarf and a little bit of the disk. And so the nice thing so the absorption lines that you see here are from the white dwarf, and we get an estimate of the contribution of the disk by looking at the bottom of Lyman alpha. It doesn't go to 0 as it should for a white dwarf. It was 100% white dwarf. So the estimate is like in the UV, the disk is only contributing like 10%. So the pulsations, even though the times with Hubble that you can observe are much shorter, you're seeing really more of the white dwarf. So the ones that have outbursts known mostly from the AVSO and VSNet, following some of these things, you can see from here that most of them don't have a lot of outbursts except for PQ and. Their outbursts are very infrequent. Their mass transfer rates, in order to see the white dwarf, the disk is very low intensity, and so it takes a long time to build up enough material to create the disk instability and have a real outburst. So when it does happen, it's huge. Most of these are 8 or 9 magnitudes when they go off. They only go off every 20 or 30 years. So you have to be able to catch them, and that's one of the problems. So theoretically, what should happen is what we expected to happen is you see the pulsations during quiescence, it goes into outbursts, the object is heated, moves out of the instability strip, the pulsation should stop, and then as the disk cools off and the white dwarf cools, just dissipates, the white dwarf cools, the pulsations should resume at a shorter period, because it's hotter now, and should gradually drift back to the quiescent period. Okay, so I'm going to show you the 3 examples that we've followed enough. First one is V455 and. This is the one that is an IP, so the power spectrum is a little complicated. This is the spin, because an IP shows the white dwarf spin. That's here, so ignore that. This is the pulsation here. The bottom level is before outburst. It's followed. The pulsation is around 337 seconds. It's broad. It's not the sharp peak. This is what JJ was talking about. The outburst happens in 2007. So for 1 year, it's followed. There's no pulses there. That's what we expected. The white dwarf is hotter. And then it gradually, at year 2, it shows up at a longer period, a shorter period than quiescence. And then by year 5, it drifts back, just following the trend of getting longer and longer. That's exactly what we expected. The only problem is the pulsations in the UV match this, but they're mostly apparent in the very hot continuum in the emission lines, which is somewhat of a problem, but I'm not going to go into that here. The second object, this is the most puzzling one that we followed for the longest period of time. Quiescence, it was followed for 6 to 10 years prior to its outburst in 2007. Here's what the spectrum looked like. It has 3 different pulsation periods that are consistently present. The UV data that we took matches exactly, and the UV to optical amplitude is a factor of 10, which we would expect for like an L equals 2 mode. So it all looks normal. The outburst went off. We've got HST data. We couldn't get it right away. We got it starting at 3 years past. Top spectrum there, bottom one is red. That's quiescence. The temperature is 14,700. At outburst, 3 years past outburst is the black. It went up to 18,000. It's expected. Then at 3 years after, 4 years after, it's the green. It went down to 16. It was cooling. That's all normal. But then the last 3 years, 6 to 10 years, it's the blue and the purple. There's 3 things right on top of each other. The mean temperature is higher, and it's all overall is the same level. Has not returned to quiescence. We tried to get data past that, and we couldn't get any more HST data, so what we've been following is from the ground. One of the most puzzling things is the first year after outburst, a new 19-minute, very long period emerged, and that is not apparent in the UV data that was taken with Galactic, but it's intermittent off and on, and then becomes quite steady. It's always there. HST we followed for the times that we had HST data. In 2010, 3 years after, the period went to 290, and just as a reminder, here are the quiescent periods, those stable ones that were present for many years. And then as the years went on, 2011, 290, 2013, 275, it got shorter, 2015, it got longer, 8 years after. And then we had Boris was able to get a whole sequence coincident with K2 data. So we had long stretches of optical ground base, and then Hubble had several points in there. And what we found is that there's a surprising, there's a 4-hour period that comes in. The K2 data is the red here. What you're seeing is the 19-minute period that was there almost all the time throughout the K2 data and the ground-based coverage that we have. The HST caught, one of the HST times caught the 4-hour rise there. You can see that large rise that was happening in the optical as well as the UV. But the interesting thing was that the short period only appears during that 4-hour rise. So somehow we have periods from 19 minutes, 4 hours, nothing, and a short period. So all these things seem to be tied together because they're all happening interrelated with each other, but none of it really makes a lot of sense in terms of what we can actually expect from following an outburst, just a white dwarf cooling in a normal fashion. So we didn't get data for several years in there because of the pandemic, because of bad weather, but the last couple of years, we've been able to get some ground-based data. So we're now at 2021, we're at the same epoch as prior to the 2007 outburst, that quiescent data that we had. But now, that year, 2021 and 2022 on the bottom, here's the light curve and there's the power spectra. The 19-minute period is still there and not the shorter periods. So conclusions are, the white dwarf has not yet returned after 15 years to its pre-outburst state. And this post-outburst is very different than the same time scale before the 2000 outburst when all the previous data. So that means that the outbursts are still affecting the structure of the white dwarf. And so we hope to continue this, but it's going to be ground-based. We keep trying to get HST data. They won't give us time to look at what's happening with the cooling. The third example that I want to show is B386 SIR. Again, we followed this object for a long time, 10 years before its outburst in 2019. It has a very stable pulsation period at 609 seconds. Anjum had an 11-day international campaign on this object, got a lot of data put together, found out that the 609-second pulse is actually a triplet, as JJ pointed out, and the spacing revealed a period of 4.8 days. So this is more typical of a normal white dwarf. The other periods that we're seeing at quiescence, because of this long stretch, we're able to see that these are actually linear combinations with the orbital harmonic, which is also very strange, which implies some kind of relation of what's happening on the white dwarf with the orbit, with what else is happening in the orbit. HST coast data, we got it sooner than we did with GW Lieb. So 7 months after it was the normal temperature at quiescence is 14.5. I went to 22,000 and then was cooling. Pulsation periods shortened, 104, 13 months, 174. And then our optical data now, so this is optical on the left, the first 6 months are typical, the same period as HST was seeing, 104. 1.5 years, it's lengthening to 190, it all looks good. The latest data we have now is 2021 and 22, 2 and 3.5 years after outburst, it's now jumped to a much longer period, 650 seconds. And so the period evolution is, there's the quiescent period at 609, after outburst went down to 100, was gradually cooling back, and then overshot. It's now sitting at 650. So here's my summary. These three systems, one looks normal. GW Lib is totally abnormal with all these periods that we don't see in any of the others. And VA36 SIR looked like it was going to a normal mode, but now it's overshot where it was, and we need to continue to follow it. So my plea to everyone is it's hard to get enough data on these systems. We need to see what is actually the normal behavior. Okay, so thank you. And there are some additional complications I won't talk about.
Questions, Barbara?
Hi, Paula. Very interesting. I was just wondering, when you talk about the outburst, were you guys able to quantify how much matter was actually ejected out? And if so, is that
ejected out?
Yeah, I mean, or
we don't. It really isn't. It's not like a nova where
like a nova.
No, the
okay.
nova. There's not enough. There's no wind seen in these.
So it is a heating process that will cause the
right.
Energy.
It's the disk. An outburst is caused by a disk instability, which dumps a lot more matter. So there's an intense amount of heating because of the increased accretion at that time.
Okay.
And the outbursts, these are they're called super outbursts because they're very large amplitude and they last for 3 or 4 weeks. And optically, G.W. Lieb stayed about a half magnitude above quiescent, the normal quiescent magnitude for about a year. But after that, it went down to the normal. So everything looks normal in the optical except for the pulsation changes. So we're really just seeing so in optical, we're seeing mostly the disk. So, but except for, I mean, in these particular systems, I mean, half the light is from the white dwarf. So we're getting some hints in the optical of what's going on, but we just get a clearer picture in the UV.
Another question, Bart?
Well, I was just wondering if, so connected to the outbursts JJ was talking about, which are different from what you're talking
Right.
about, potentially these pulsators have that same sort of pulsational outburst phenomenon in a certain range of temperature. And I wonder if in the past, before we knew about the outbursts in the ZZ SETIs, if they would have just been discarded as, oh, the disk is doing something weird, and I wonder if you see any signatures of that, and potentially because of the quick evolution in temperature, this could be a phase that we see them go through.
Yeah, I think the problem is you have to have enough time series to actually look for some of the things that are showing up. And I mean, we've got some data in K2, and there's a lot of structure that we see in just quiescent periods of dwarf novae, and we don't know if that's related to the disk or related to something that it's not as. I mean, really, the things JJ was talking about are it's quasi-periodic in those times, right? So and the structure in disks is not periodic. That's why, I mean, for a long time we thought much of this phenomena might be like the 19-minute, could be something in a disk, but we don't see disk phenomena that are stable over years. And so the only explanation we have is that it has to be something connected to pulsations. And we haven't made that connection with a lot of the phenomena that's seen in time series of dwarf novae, because I think most of them are dominated by the disk. You have to select the systems that you're seeing a good portion of the light from the white dwarf, and then maybe some of that stuff will show up.
Okay, last question, Ken.
Hey, Paula, I was just wondering what the rotate. I'm over here.
Where are you?
To your left.
Let's see.
To your left, yes.
Oh, okay.
What the rotation period does after the outburst.
So what does the rotation for
any of them?
We see the rotation periods from the width we're fitting the UV lines. That's how we get the rotation periods. So for the one that's magnetic, we have the spin, and you can see it. That's nothing happened. You could see the spin right through the outburst, and it was right on.
Okay, and the other ones,
we don't have a good handle on what the rotation is, other than the fitting of the lines. So we don't have like time series of the rotation.
Okay, so the pulsations don't show splitting.
Oh, well, that's the only one that we've followed for 11 days to get enough information to see the splitting. Now, G.W. Lieb has also seen the splitting at quiescence, but there wasn't enough during the outburst to put that together. But I will say that in B386 SIR, the 609 second, the UV data in the fitting of the model fitting also gives a rotation of the atmosphere of 200 seconds, 250 kilometers per second, which is just, a few minutes. So there has to be, if the 4.8 day from astroseismology is correct, there has to be differential rotation of the atmosphere versus the core.
Okay.
Okay, yeah.
Okay, maybe Mike, while we are fixing Morgan.
Yeah, I just had a
Paula,
comment.
can you answer, Mike?
Just a comment and a question. So of course, when the star heats up and you see very different modes, you see big jumps in period. But when it settles on one mode and goes from 512 seconds to 511 seconds, that's probably due to the cooling of the whole thing. And there you could get really interesting information on how it's cooling off as a function of radius.
Well, I'm not sure I would really trust those, 1 second, because there's really such a spread in it's like the mode, what's the term for it? Because the mode is what, even the 19-minute that we typically see in one of the others is a spread of, 1190 to 1220 seconds that's there. So I don't know if we could get that accurate enough to tell.
And the other question is, during an outburst, do you know how much mass is accreted?
I think Ed Cyan worked that out for GWLib. I'd have to look it up. I don't have the number off the top of my head.
Okay, well, thanks, Paula, again.